Hello and welcome to Lab 4, the Superior Spring, also known as a hair tie. The objective of this lab is to find the spring constant of a spring constantly on my wrist. Right about there. So essentially, I just thought that was a spring in my daily life and might as well know some unnecessary information about it. To do this, I will first review relevant formulas and concepts with you. Next, I'll find varying measurements of the spring length in both relaxed and stretched states and calculate the spring constant based on this. Next, I'll analyze how this spring constant may change over time. So, relevant formulas and concepts. We start with the energy principle. The change in energy is equal to the sum of the change in all of the energies, which is also equal to work done on the system. The force of the spring is equal to the spring constant, which we're looking for, times the stretch of the spring. Weight is equal to mass times gravity. This is important because I'm not capable of measuring mass, so we just have to calculate it based on the weight. Please note that for the force of gravity, these are equal except the force of gravity is negative. And so with this information, we could make a few free body diagrams. The force of the hanging is holding the hair tie up and equal to the force of gravity because the system is static. It's a static here as well, and so these values are still equal to each other. The force of the spring is pushing up as the force of the mass pushes it down, so these would also be equal as seen here. You could see this in terms of the energy principle written out here as well. And so you could set the force of gravity, or the force of the mass, whatever you would like to call it, equal to the force of the spring. Please note this is the same as weight. So for gathering data, I decided apparently that hanging scissors from the ceiling was the safest option. So the weight of the scissors is something I was just able to find online. It's 85 newtons. The initial relaxed length of the spring is 0.24 meters, and the stretched out spring is 0.27 meters. Please note to measure this, I used a string and wrapped it around the hair tie and then measured it with my ruler because my ruler couldn't bend like that. I didn't have one of the ones you'd use for fashion. So calculations for K and conclusions. So as we know, weight equals mass times the gravitational constant. This was unnecessary to calculate because you see the 0.085 newtons was used again right here because you had to go calculate it again. Right here I found the stretch, so the relaxed length is right here and this is the stretched length. So this value times the spring constant equals the weight. So I just divided the weight by the stretch to give me 2.5 newtons per meter. So what if we did this but for a new hair tie? Because you see right here, my old hair tie is pretty stretched out. So how is this number changing over time? To find this out, I followed the same process for the newer hair tie as seen right here. And so I got the spring constant of 1.35 newtons per meter. You'll notice that this number is about half as stiff because as you increase that number, you're basically saying the spring is increasing in stiffness. I believe this may be related to an error because as you could see here, the spring is very stretched out to an extent that it's reaching its limits. And this really shows that over time, that hair tie or spring will lose its stiffness after extreme use. Obviously, human error may also be a factor. Using strings in this way is not an exact science, especially with such detailed data. But overall, I think it is a valid conclusion that over time, I believe that the hair ties will decrease with regard to their spring constants. Thank you for your attention, and I hope you enjoyed this lab.